Hello everyone, my name is Adrian de la Cerda. I'm going to be talking about the thermal analysis of a microchip and heatsink. It's a a lab report that we received in school, and I did a technical report on the subject. To begin, a little background about myself is I am a fifth year engineering major. I transferred from a school in Tennessee called Milligan University. It's a small private Christian university. I'm passionate about thermofluid sciences and manufacturing. I've had two internships, so both of them in manufacturing field. But as a mechanical engineer, thermofluid sciences is a big, strong suit that we have to have. My hometown is Brownsville, Texas, one of the poorest cities in the nation. I want to work in the green energy sector or aerospace. In fact, just recently I picked up a internship that's NASA sponsored in San Antonio, and I will be working on propellant dynamics of launch vehicles. So my target audience today is number one, engineering students. Engineering students in any platform, any major, across any school. It doesn't have to be A&M Kingsville where this problem is sourced from. Second, CAD-related businesses or majors. Like I said earlier, any major having to do CAD analyses or FEA analysis or businesses. There's people out there that don't know how to use Solidworks and only use AutoCAD or only know how to use Fusion 360. And the third one, like I said right now, anyone willing to learn, anyone wanting to adapt and go outside of what they're comfortable with is my target audience. So why this topic? So number one is frustration. Frustration can set in when you're doing this analysis and it's due in 2 days and you can't figure it out. You're trying your best and it's not necessarily that you don't know what you need to do, it's that you don't know how to do it within the software. So that's the lack of knowledge as well. Lack of knowledge of knowing where to click, knowing what steps you need to take and things like that. Time savings is due 2 days from now and you have 4 problems to do. It's having the understanding and knowing what to do is that time saving efficiency, not wasting your time having to search for what is what and how to do what, and hands-on learning. This presentation is a step-by-step guide, and so it's not necessarily just giving you what you need. You have to do it yourself. So before starting this problem or any other problem that you will have to do is you need to install SolidWorks. If you're located in Texas A&M Kingsville, you can get a license to the program at the Mechanical and Industrial Engineering offices on the 3rd floor in the engineering complex. If you're not, look into it for your own school and if the school provides it or the program that you're in provides. If neither are applicable, then there's a student version, or you could go to the link that's provided here or provided in the comments section below. Yeah. So now that you've downloaded the software and installed it onto your computer, understanding your problem statement and knowing what parameters you have to work with is key for a successful simulation. Below are the parameters that we will be using in the simulation, as well as some direction on what information you will need to pull from it. So the heatsink is made out of 2 parts, a ceramic microchip and an aluminum radiator. The microchip generates 30 watts of heat, the ambient temperature is 30 degrees Celsius, and the thermal resistance is 0.002. All these will be put into SolidWorks, and I will show you how. So some of the things that you will pull from the results is the temperature profile and the heat flux, as well as the heat source, the convection, where you put it in, and the correct contact. So now that our problem statement is addressed, it is important to understand what is heat transfer. So heat transfer can be transferred in 3 ways. One through conduction, which is through solid objects, through contact. Convection, which is within fluids. In our case today, we will be using convection. And radiation, transfers through the electromagnetic waves without involving particles. And as you can see here, the fins are exposed to air. So if you were to be doing a different analysis, you would use conduction. But in our case, since we're releasing and transferring that heat through the heat transfer device into air, we will be using convection. Here is an example of several different heat transfers and cases. If you would be doing a hand calculation, it is important to do this hand calculation because sometimes you put in wrong values into Solidworks. And so having that background and having that hand calculation that you can see every single step and every single result is important to double check. So to begin this simulation, we're going to want to open up the expanded view, which is circled here. Without this view, it would be difficult to kind of get within. You would have to hide parts and unhide them. But here, kind of, instead of being contacted, they're spread out, even though in the simulation they will be run as contacted. This just makes it easier for us to see within and what happens and how to contact and where to put in the power. Next, you will start up a study. So we will create this terminal simulation, locate on the top right of your screen, and you will select thermal. You don't need to click 2D simplification, and then you will click the green arrow to process. So next, we will bond and add a thermal resistance to complete the connection from the chip to the radiator. As you can see, the expanded view helps us view the internals and where to bond and where to add. So you're going to want to click local interactions on the left picture. On the middle picture, you will select the faces of the corresponding area. You will also want to click the distributed load, as the units do not match if you do use total. And you will input that 0.002 value. So next we will apply what power to the microchip. Located under the thermal load tab on the left side, click on heat power and select the microchip component. Next, you will add the amount of power that the chip will produce and place it in the reverse direction. So as you can see in the most left picture, the thermal loads, then the heat power, and you can see the drop-down menu with the heatsink. You will select that microchip and click on heat power to input that 30 watts that it will generate. So next, you will need to apply the convection properties, which we talked about earlier, to the fin section. Keep in mind that when you apply the property, you will need to apply it to every phase of the fin, allowing for the most accurate depiction of surface area contacting the surrounding fluid, which in our case is air. And in this case, our air is ambient temperature, which is 303.13 degrees Kelvin. As you can see from the most left picture, the thermal loads will open up the menu where you will click Convection. And as you can see in the most right picture, every single phase is covered, and every single phase is in the entity selected. You will put in that 25 watts per meter squared Kelvin, and also that 303.15 Kelvin for ambient temperature. So the last step, and arguably the most important step before running the simulation, is the mesh. The process of subdividing the model into small pieces is called meshing. So finite element analysis, or FEA programs, look at the model as a networking of interconnected elements. The finer the mesh, the better the result. In our case, you can see here that it spans 3 across every single load. In our case, this is fine enough. You could go finer if you would like, but this is just right. On the most left picture, you see the Mesh tab. You will click it. It would open up the middle picture, and you will click Create Mesh. You will have to open up the mesh parameters and select Blended Curved Base Mesh. You will select the mesh size of 4 millimeters per node and 16 millimeters round. And finally, once completing the mesh, you will be able to run the results. Running the results is the easiest step. You just have to click on the thermal tab and select Run. This should pop up. If it says that it failed, you probably have an incorrect input, and you have to go back and repeat the steps again. So now that you have the results, it is important where you get the information from. So there is a report tab that is on the top of your screen. Should be below where the document name is. and it is important to know what we need. So as spoken about earlier, we're going to need the contact information, the heat flux, the heat load, and the temperature profile. All of these can be pulled from this report that is generated by Solidworks. So this is the heat flux. As you can see here, you will have to look at the direction and make sure that it's flowing from the chip into the radiator, and the minimum and maximum values of such, and where they're located. So this is the heat load tab. This is just making sure, and you have to pull this and add to your report, that your values are correct and that they're placed in the right spot, as well as the temperatures, the convection, and heat powers are all selected in this. This is the temperature profile, which is pulled from that report. We can observe the temperature distribution on this slide. Finally, these are my references used and cited within the text.